that maybe we can do something more useful than puzzles. So the topic is inequalities. And why are we talking about inequalities? Because it's pretty much everywhere. It's in approximations, it's in optimization, machine learning, mathematical analysis, and pretty much you can call inequalities to be the backbone of mathematics. The topic is so lovely because you can, even a mathematician like G.H. Hardy can work on inequalities, and even somebody in class 7 can also be thinking about inequalities. So it has wide audience, meaning anyone can try something on that. And meaning it's a lot of manipulations at times and intelligent manipulations. So why? I mean, although it is in real life, I mean, a real given academia and given industry. So the thing is, think about how you would normally you have all these kind of algorithms like Prim's algorithm, Kruskal's spanning tree algorithm, and so on. If you remember, how do you prove that they are optimal? And please feel free to interrupt with questions. So how do you think? How do you prove an algorithm to be optimal? Dynamic programming is a difficult beast because dynamic programming just goes ahead and does it. It does not say, hey, most optimality proofs involve some other concept like a certificate. If you guys are aware of what NP completeness means, essentially you think of a certificate that, hey, I am able to achieve so much. I know I won't be able to achieve below that amount. So that would be a certificate of optimality. So typically when you have those certificates, that's the typical way we want to target optimality. And dynamic programming is therefore, again, to call it out, very, very surprising. So what you do is, most of the proofs that we know of optimality of something, they talk about a lower bound. Essentially a lower bound for the resources that the algorithm takes. And here we sort of assume that we are talking about a minimization problem. So therefore a lower bound makes sense. So I take an auto or I take a Uber, and the Uber says, hey, I'm going to be able to reach from Malleshwaram to here in 10 minutes. And the auto says in 15 minutes. And maybe there's a lower bound. The roads, the flyovers, they already give you a lower bound. So if somebody says, hey, I'm going to be dropping you there in 3 minutes, okay, that's not going to work. So, and this is a minimization problem, right? Of course, if you are talking about maximization problems, like maximize the amount of profits I make. So typically there are two kinds of people. I think Suprabhat and I have spoken about this earlier. You can either be a minimization type, you are minimizing your losses, or you can be a maximization type, you are maximizing your profits. So anyway, I think of myself as more of a minimization type. I always try to cut down losses. So bottom line is, whenever you are talking about all this, upper bound or lower bounds, you are essentially proving inequalities, whether you know or whether you are aware of those or not. Okay, let's start with some simple examples. So you are given n real numbers and they happen to be non-negative, positive in fact, and their sum is at least n. And you have some statement here. Let's look at the statement, what this means. Oh, sorry. So what this, okay, never mind. Okay. What this statement means is, of course, you know that not all xi's can be very small. Some of them will have to be somewhat large, right? I mean, the question is, can the situation be that bad that only one xi is 1 or higher? So first of all, the first observation you make is the average of these n quantities divided by n is at least 1. So the mean or the average is at least 1. So therefore, it may be a pathological case where there's exactly one variable which gets the value 1. Okay, that's a bad case. But here's the question that, is it true that suppose I slightly move away from that 1? 1 seems concentration at exactly the mean. Maybe that's not happening. But if I slightly move away, and I will talk about what moving away means here. If I move away from 1, I ask, okay, what are the variables? Which are the variables which have value at least half? And thereby you see that this is, the question says that if I allow myself, if I say that, okay, think of a corresponding statement where summation over I, where xi is at least 1 xi. I won't be able to make any comment there. The comment which I will be able to, if this half were actually a 1 and greater than were greater than or equal to, then I would be only able to say the lower bound on that quantity is 1. Because I may not be able to find even a second xi which is 1 or more than 1. It can be that bad. But more, you can get more structure into the problem if you slightly relax yourself. You relax yourself and say, hey, I'm not asking for something so severe, xi at least 1. Instead, I'm looking at xi at least half. And there you see that there's a lot of mass. By mass, think of these xi's as weights. Sum of the weights is at least n. And then this statement reads is that if you are allowing yourself to move away from the mean slightly, most of the mass lies among these xi's. So of course, there may be some xi which is 0, some xi which is 0.25, but they don't account for too much of the mass. One can of course say, what do you mean by not too much? Because we are only able to prove greater than or equal to n by 2. But whenever we talk about a lower bound, we sort of exaggerate and say that, okay, this contains most of the mass. If it's a constant fraction of n, I mean, that's typical what we do in computer science or math. Okay. So let's go over the proof is quite easy. What I wanted to pinpoint is that this is the way you can read such a statement. Don't bother about the proof at all, but let's go through the proof. So the proof, as you can guess, doesn't do much. You are talking about I for which xi is greater than half or less than half. And by the way, these problems all came from some paper or the other in approximation algorithms. And the latter problems are motivated by more machine learning and optimization. So you can break up the sum into these two parts and say that, okay, everyone is okay with this step, pretty much brain dead. You are just starting to work or engage with the problem, nothing more. But now you just say, okay, I am not able to get a good handle on these guys, xi less than half. Because these xi's may be very, very small. They may be 0, they may be 0.25, they may be 0.49, whatever. I'm not getting a handle on them. So let me try to replace them by some proxy measure. A proxy measure is the count, the number of items of that type. So motivated by that, so from this step, we are going to this step in a way that I don't have a very good handle on this, but each of them don't contribute too much to the overall sum. So therefore, I am going to sort of measure them by the maximum they can be. By the maximum they can be is half. So therefore, I now have reduced the problem of estimating this by a count. So I just need to say if k denotes the number of terms such that xi is less than half, then this holds. Everyone is okay with this step going from here to here? I mean, there's a very, very, very small leap that, okay, instead of this, I can just replace all of the xi's by the half, and then that becomes k by 2, where k is the count. And now it's pretty easy. Now you rearrange, starting with this end and this end. You take k by 2 over to the other side. So n minus k over 2 is less than or equal to this sum, and that is greater than or equal to n by 2. Okay. That's because k is the number of terms and n is the total number of terms. So k is less than n. This k by 2 is something less than or equal to n by 2. So therefore, what you are leaving behind is at least n by 2. Okay. So there's nothing pretty much going on. This is just a warm up. Okay. So the summary now. The mean is at least 1 given the n numbers. And maybe there are very few numbers which have xi approximately 1. But most of the mass, that's what we are calling, most of the mass is around that mean. Mean 1, you go away from the mean, you stay at half and beyond, half and above. Most of the mass, n by 2 of the mass, practically half of the mass is in this region, is in this zone, okay? So, just to forward the story slightly, how many of you are familiar with, say, Markov's inequality? Okay. Chebyshev and Chernoff? Telegram. Okay, okay. The list can continue. But can anyone mention what those inequalities are talking about? Say, for instance, can anyone state Markov's inequality? Anyone? It's okay. It's okay. I mean, we are going to cover it anyway or not cover it. So, don't remember. So Markov's inequality is essentially a very simple statement. It takes a non-negative random variable and then takes the essentially the probability. Because it's non-negative, it does something. I can use that, or I can use here. Does this strike a bell? What happens is probability that x is at least t for x a non-negative random variable, and therefore t also non-negative. Otherwise, the statement is the probability that x is greater than or equal to -1. That probability is always 1. Don't even bother about it. So t in order to make some sense out of such a statement, t better be non-negative also. And then you have e of x, the expectation of x by t. The proof, if you see, is really, really trivial. If this were not the case, then this could not be the expectation. If all the quantities, if all the values of the random variable, a random variable is sort of a function. If all the values, if all the outputs of the function are sort of on the lower side, then the expectation cannot be e of x. It has to be something smaller than that. So this argument is sort of like that. So here, e of x is the mean. And you think of t as, I don't know, twice e of x. Okay. If t happens to be twice the expectation, then Markov says probability that x goes beyond. First of all, here's the expectation and goes beyond the expectation by another e of x is at most half. So think of this also as a concentration of measure. So Markov says for a non-negative random variable, most of the mass is concentrated around the mean. And Chernoff, so there are other statements, Chebyshev, Chernoff, and so on. They are progressively making bolder statements, sharper statements about this. This is taking a random variable, which the only property it has is non-negative, and you make some conclusion about that. Okay. So we'll come to that later. So now let's go over to the another similar inequality. This is talking about graphs now. Again, this appeared, I think, if people are familiar with approximation algorithms and this specific problem of a feedback arc set, this I think is from that problem. This appears in the analysis of one of those problems. So, okay. So here we are given a digraph. Normally, you know a graph as V, E, vertices and edges. And here we have a digraph V, A for A standing for arc, ARC, arc. And there are some definitions here. IV denote the in degree of the vertex. DV denote the total degree, in plus out. And this is what we need to prove. Okay. We are going to skip the proof here. So what I want you to appreciate is that this, what was the first thing? We took n numbers, they had a mean, and we said that the sum of the numbers such that the numbers are at least half is sizable, is at least n by 2. The only botheration was at least. So here also there is a similar flavor, okay. The flavor is some at least kind of statement is coming along. And again, so in order to map this problem, I know this is a lot of text to digest right now. In order to map such a problem to the previous one, think of what those xi's were. Those xi's were saying x1 plus x2 plus xn is equal to, is at least n. We don't have such a clear statement here, but you can think of a proxy as IV by dV is at least 1/3. Remember, in that world, we were taking those xi's which were at least half. Here, similarly, what we are doing is, we are taking those vertices of the graph for which IV by dV is at least 1/3. Huh? Sorry? Okay. So, everyone more or less okay with the problem as to what's going on? So the problem is sort of weird that, okay, I have a graph, it's a directed graph, and now I am looking at some special vertices in the directed graph. Then, you know, in a directed graph, there can be a sink. A sink has, everything is in degree. IV is equal to degree of V. Or it can be a source. If you have a DAG, then there's a source. A source has IV is equal to 0. Okay. So just to get a warm up about what the problem is talking about, it's saying that if you look at some special vertices where there's a lot of in degree, lots of edges coming in, if you focus on those vertices, then if you focus on those vertices which have a lot of in degree, they account for a lot of edges or lot of arcs. Okay. Why? Okay, I want you to think about what's surprising or not surprising. First of all, symbol soup, so therefore it may not, it's harder to appreciate what's going on. So first of all, think of this as a lower bound, okay? These IV guys, these are all incoming edges. Those IVs are surely getting counted here, right? So each of these IVs are pretty large. Maybe that corresponding vertex has overall DV low. That may be. But so that's the surprising part. That okay, what if DV were only 1? Then IV is also lower bounded by 1, right? 1 by 3, and IV cannot be 0, so IV is 1. But essentially, what I want to point out is that this sum surely has all of these IVs in it. So therefore, you can replace, if you want to do a very, very, very dumb calculation, what you can surely do is, I can replace this summation over these special vertices of D of V by summation over those same vertices of the in degrees, okay, summation IV. And that would give me a weird kind of sum. That would give me, again, the summation V over V1 of dV, now with a by 3. Okay, so that's not very useful. But what I want you to appreciate is that we are surely on track for a lower bound. Because there is a lower bound on IV, surely when we start the manipulation here, we would be looking for a lower bound. They would have enough edges in there. I mean, it's great that the lower bound happens to be as strong as the total number of arcs in the graph by 3, a constant factor away from the total number of arcs in the graph. But yeah, roughly that's the flavor. You are looking for a lower bound for sure. And the proof is sort of very similar, meaning with some extra masla. The proof essentially has that, okay, here's one statement, here's another statement. dV, summation dV is equal to twice of the arcs, because this is what happens for a graph. Summation over the degrees is twice the number of edges. And this is the other statement, summation over IV is equal to size of A. Because every edge gets counted once. Every pointing edge, directed edge, is counting 1 to the edge, to the vertex for which it's an in degree, right? So I am not going to go through this. I mean, this is sort of, if one can try it out. So these are, the idea is similar. The idea is very similar. Like there we separated out xi at least half and xi less than half. Here you do a corresponding, the separation is given to you. The separation is right here, right? V in V1 or V in V minus V1. So you do that accounting and you do some more calculations. The concept, conceptual understanding of the calculations is clear, that you separate them out on, what is crucial here is that there are two facts, okay? So these two are sort of very important, that one is twice of A and the other is A. But bottom line is that you get this, okay? So this is one of the, I was asked by Adirup about some quiz questions. So this is the first one. I mean, if you wanted to try, and if you have not been, if you have been sleeping till now, okay, you can try this. Okay. And so this is the question number 2. so this is what we showed or did not fully show, and the by 3 becomes by 2 by sharper accounting, and then this by even sharper accounting, you have at least, I don't see anyone writing anything down. Nobody is going to try it. Okay. So let's go to the motivation again. So the motivation is this, that if you have summation dv, summation of the degrees across the whole graph is equal to twice of the summation of the in degrees, right? So on average, IV is roughly half of dV. I mean, these are very vague comments. On average, IV, I mean, essentially I'm just taking the two here and saying, okay, comparing term by term. Of course, that may not happen. That one IV may be very close to dV, another IV may be very small compared to dV. And that is why, in average, so think of this statement as saying something in aggregate or in average. So on average, IV is roughly half of dV. And that's the marker. And we move away from the mean and ask how many vertices V will satisfy IV is at least dV by 3. Like in the previous problem, we were not able to give a count. Give me the count of the guys who are at least half. We did not do that. All we could say was, take the guys who are at least half, their total mass is at least n by 2. Similarly here, I won't be able to give you a count for the, it can be very pathological once again. There may be only 2-3 vertices which are accounting for the whole thing. So while I won't be able to give a count, we will get a result for the overall mass again. And these statements are statements about the overall mass, right? Okay. So going back to the broader theme, so these are very specific examples of concentration of measure. The broader theme is Markov should come first and then Chebyshev, because Chebyshev derives from Markov. Chernoff should of course come in the place where it is, and Talagrand comes last. So these are all essentially you take a bunch of random variables x1 through xn, and then how many of you are aware of Chernoff bounds or something like that? Okay. So bottom line, what is happening is that when you work on machine learning, right? So suppose you have some classification algorithm with you. So there are two things which sort of add on a classification. How do you figure out how effective the algorithm is? So one thing that you look at is the bias, and another thing that you look at is the variance. So for instance, you can have a classifier with low variance and high bias. Essentially is that it never, the mean on average it's very, very good, but individual predictions are way across the space. At times it's telling you some prediction here, and so on. So that is a high variance and low bias classifier. That's something which we don't want. I mean, when I want to make the next prediction about whether there will be rainfall or not, I don't want you to be saying, hey, over 30 days I'm going to be correct, but tomorrow I'm going to be wildly off. That's not good. Similarly, so these kind of, the motivation for all that, meaning why we study these inequalities, are these actually help in that regard. So there is, okay, I'm finding it slightly harder to describe this. Let me see. So suppose I have two, I can write on that. Okay. So, okay, I can state the question in the meantime. So suppose I have two, oh, they were right here, sorry. I have two random variables, okay? And suppose they are like normal random variables. What does that mean? A normal random variable, I mean, you can, I just need a name to attach to it. You can think of any random variable that you want. But think of them as, maybe they are coin tosses, okay? So suppose this one has, everyone okay with what bias is, what expectation is and what variance is? Yes? So suppose the expectation, both of these are draws, these are IID. independent, identically distributed, independent, identically distributed. Okay, so suppose these are IID variables. What that means is they both come from the same distribution. Okay, so that means both of them have the same mean, and both of them also have the same variance. Okay, some sigma squared. What do you think? So these individual variables, they have their variances. Okay, so their mean. So maybe if you plot out x1 looks like this is the mean. This may be the mean, and this is what's accounting for the variance, right? What do you think happens when you sum the two variables up? Suppose I now consider x1 plus x2 by 2. Okay, by 2 is averaging essentially. You are taking the average of the two random variables. What do you think happens to this? The expectation, of course, if you remember linearity of expectation, the expectation happens to be mu. Okay, and what happens? This is a modified random variable, right? This random variable depends on the earlier two as sum by 2. What do you think happens to the variance? Louder, and anyone? Sorry?
Yeah, 1 by root 2 of sigma square.
Sigma square by 2 or sigma square by square root 2? Sigma square by 2. So basically, sigma squared by 2 is the variance. I think you are thinking of the standard deviation. Standard deviation will be sigma by square root 2. Okay. So what has happened is, just by taking a sum and dividing by 2, taking the average, you seem to have magically sort of half the variance. So that's a very powerful statement. The powerful statement is that when you have a classifier, again I'm talking about this, if you are uncomfortable, think of predicting rainfall. Think of our med department, okay? So they are predicting, oh, today it will be raining this many millimeters, tomorrow that much, and so on, okay? And they perhaps have high variance. Suppose we took another independent med department, and then we added the two results up and divided by 2, we would be doing better. We would be having better predictions. Okay, so that's the direction in which Chernoff, Markov, Chebyshev, Chernoff inequalities, Chernoff bounds go in that direction. They are trying to talk about concentration from the mean of the average of n variables, n IID random variables, x1 plus x2 plus xn. I don't want to dwell too much on this because we are not going to be doing much. So I want to just state what Chebyshev is. How much time? Okay, I see. Okay, so let x be a random variable with e of x is equal to mu and so on. I mean, if you already are not bored by this result, forget about it. How does the proof go? The proof, what do we know? We know only Markov. We came into this world just now and we know only Markov. I want to apply Markov to everything. So therefore, oh, Chebyshev is coming along, so I'll apply Markov. So how do I apply Markov? Markov applies only to a non-negative random variable. So what I do is, I take x minus mu and square the thing. Because if I square it, it becomes non-negative. And this is, I don't know, there's not much intuition here at times. It's more like you tried a smart manipulation. This is a smart manipulation which Chebyshev or someone did, that x minus mu squared is greater than or equal to t squared, is the event for which I want to find the probability. So what is the expectation of x minus mu squared? By definition, that is the variance. Okay, so by definition, expectation of is equal to, this is by definition. So therefore, one can easily see how Chebyshev follows. Expectation of x of that modified random variable is sigma squared, and this t has become x minus mu squared greater than or equal to t squared, so the t squared falls in the bottom. Okay. So, and the question was, how do we prove it and how do we prove Markov, which we already talked about. And now problem number 2, again, if you are interested, is that a one-sided version. So what happened between Markov and Chebyshev? Markov was easy to prove. We did not talk about the proof there. Chebyshev was very, very easy to prove, given Markov. Let's slightly change the game up a bit. There's a one-sided version of Chebyshev, where essentially, if you see this event talks about essentially 2 events, x minus mu greater than t, or x minus mu minus x greater than t, okay, depending on the sign of x minus mu. And this one-sided inequality applies, basically this may be too weak to apply for certain settings, and you want a sharper inequality. You do see that this is sharper, right? Because I am talking about a smaller event, it's pretty much roughly half the event, but I don't get sigma squared by 2t squared. That's a bit too much to ask for. That because x minus, so this event, x minus mu greater than t, this event is essentially composed of, is the union of, disjoint union of 2 events, x minus mu greater than t, or mu minus x greater than t, right? So it's unlikely that both of them will have equal mass, will have equal probability mass. So therefore, surely I can't expect a statement like sigma squared by 2t squared. That's of course the best kind of result that I can get, but I won't get that. Instead, what you are able to prove is sigma squared by something, instead of by t squared, you see something larger than t squared. So that at least a sanity check says that this quantity is not as large as this quantity. If I am taking a sub-event, and if I were able to give a bound which is worse than this, then that's very, very bad, right? So this is one more problem. It's again slight manipulations with x and mu and so on, okay? So when are they supposed to work on that? Later or now? Oh, those kind of questions. I was under the impression that they will take them back home, come back the next day. Oh, these were supposed to be questions right now. Okay, then I'm going to ask something else. Okay, okay. Okay, this is becoming worse things to be asking short questions on. Okay, okay. So now we are going to change gears, as if all that was not enough. We are going to change gears slightly, and we are going to give some idea about a different kind of inequality. So how many of you are okay with arithmetic mean and geometric mean? Great. Somebody please state arithmetic mean, the AMGM inequality out. Anyone? Okay, somebody state what arithmetic mean means.
It's okay. I mean, if you want the questions, I mean, if they can answer the questions tomorrow.
They can answer the question. They are just not answering them.
I mean, they can answer the questions, those questions tomorrow also. That is also fine with us. Okay, if you want to answer it tomorrow, email us. Okay, that's fine.
Okay. So so this is going to get into slightly drier territory, but again, how many of you are motivated to get into machine learning? If I may see a show of hands. Some of you are already in machine learning and you did not raise your hands. Good. And how many of you would like to work on optimization or approximation algorithms? Okay. Then all of this is very essential. Others can sleep. Okay. So you have what is an optimization problem? We are continuously solving, all the time in India we are solving such problems. Do I buy sabzi first and then go for the fish, or do the other way around? I have to minimize distance, that, and so on. So some of the constraints which you get in life are hard. Some of them are softer constraints, easier to solve for. So that's roughly what an optimization problem in the framework that we are talking about is. Okay, has an objective and has some constraints. Okay, does anyone recognize this problem? Somebody from that side, does anyone recognize this? This is a formulation of one of the problems that we study, I think, in first year, second year, third year. Okay, so this is called. I haven't given anything, right? I have put a V and I have put a E. So chances are this has to do something with graphs, and this is what is called the vertex cover problem. So vertex cover problem again is a very real problem. So there's a very cheap government, and the government wants to place as few traffic guards as possible. So what they want to do is the traffic police that they place on the roads, a traffic cop at an intersection can see all the roads of the intersection. We are assuming he has 360-degree view, but okay. So that's what a traffic cop is, that he can see all the roads which are intersecting there. Now the question is, what is the minimum number? That's the number question. What's the minimum number of traffic cops you need to place on the intersections of Bangalore? Okay. So the intersections of Bangalore, okay. So that's what is, so what are we doing here? You are thinking of the road network as a graph, and the intersections being the vertices of the graph. And you are asking, what is the minimum number of vertices I need to pick up so that all the edges get sort of supervised or covered, okay? So this is called the vertex cover problem, okay? If you have seen it, well and good. We are not going to be dwelling on this. So this problem is pretty easy to solve. Easy to solve in the context of it's of course NP hard, but easy to solve from the point of view of an approximation algorithm. I mean, I won't be able to give you the best solution, but in a very, very short time, I'll be able to give you a solution which is almost optimal, a factor of 2 away from optimal. If the optimal cost is, I don't know, 100 rupees, I'm going to give you a solution with cost 200 rupees, not worse. Okay. Questions? Okay. So that's a problem where all the constraints sort of are soft, as in they are not hard. I can solve that problem. Typically, when you move on with regard to problems, the problems become harder, and people looked at what is called the partial vertex cover problem. That these are the roads which are important to me, or rather the government gives up, says that, hey, I don't have money enough to monitor all the roads, but I will give a sort of agreement with the public that I'm going to be monitoring K of the roads. Some 100 of the roads I'm going to be monitoring. So for that, you write another linear program. These things are called linear programs, some optimization program. And then you realize, okay, now there's a bump that you are not able to solve this in the same way you are able to solve the previous problem. And just to motivate, what is a soft constraint and what is a hard constraint? Without this constraint, I was able to solve this very nicely. But with this constraint, life got messed up. So soft and hard are very vague comments, very vague names. Essentially, when you are solving optimization problem, what do you call soft? What do you call hard? If you are a very smart guy, maybe everything is soft. Everything is a soft constraint for you. But if you are not, some of them are hard constraints. Okay. Now what you want to do is, now comes the major thing about life is hard. What do? You have these hard constraints. You want to pull them into the objective. What does that mean? And this is again meaning the central theme of all of most of approximation algorithms or optimization is that if you are facing a problem which is very hard, find the right relaxation. Relax yourself. Drop a constraint. See if you can solve without that constraint. That's the way we normally learn also, right? We don't learn a thing end to end. We break it down that, okay, this is what I understand, and then a baby step forward. So similarly here, what you want to do is, you want to drop the constraint. And you want to sort of pull it into the objective, which is vague. It will become clear from the next slide. So let's talk about a general optimization problem. You have a optimization, your objective is f of x, and s for soft, s of x less than or equal to 0, h of x less than or equal to 0, hard constraint. Okay. So the thing is that I want to point out, if you have written down these kind of programs for yourself, you know that when you talk about a minimization problem, I am minimizing my traffic time Subject to, I need to get there in at most 10 minutes or something. That did not make sense. Okay, I want to minimize my total cost of purchase such that I buy at least 5 potatoes. Okay, at least 5. So there's a potato constraint which says number of potatoes has to be at least 5. So if you notice here, we are writing the constraints in the sort of other way. Instead of writing minus h of x greater than or equal to 0, I am writing exactly the other way, h of x less than or equal to 0. There is a reason for this, it will become clear. But just that this should be a call out. One should notice that this is not the usual way we write down our programs. Okay. So this is what we call by pulling something into the objective. So what has happened is that h of x, that constraint, which was supposed to be at most 0, okay. And now for the next 2-3 minutes, I'm going to jump between this and the previous slide, okay. So what we did here was, we took that constraint h of x and sort of pulled it into the objective. Pulling actually means the physical act of, it was here, I pulled it up. The objective, I wrote it up, that's all. So, and I put a lambda there, okay. That lambda is mysterious, let's understand that later. So, what happened? So here was, think of something which makes this kind of a program feasible. Suppose somebody gave me a x for which h of x is at most 0, okay. Then that same point, the same x would still be feasible because I have dropped some constraints. I have made my life simpler. I can't be doing this today, so I dropped that constraint. So therefore, the same x would surely be feasible for this. And if you notice what happened to the objective function, the objective function did not increase. So it may lower, but it did not increase. Why may it lower? Because for that point x that we chose, h of x may be -1. And that is what we plugged in there, lambda times h of x. So lambda times that -1 is making that objective lower. At the same point, so what are we saying? A feasible point, what we call a feasible point is a point which satisfies all of these constraints. A feasible point here surely is feasible for this with a correspondingly perhaps lower objective. Okay. So that's the meaning. It may sound very trivial, and this, by the way, sounds really trivial, and it has tremendous consequences. I mean, lot of machine learning algorithms keep on falling back on Lagrangian relaxation. The takeaway is that if there are hard constraints, whenever somebody gives you a problem and you realize, okay, there are some constraints which you are not able to solve for, think about Lagrangian relaxations. That, hey, can I eliminate the constraint by, in childhood, what we did was, if you remember how we used to solve simultaneous linear equations, we would eliminate variables to make our problem simpler, to make our problem on 2 variables from 3 variables. So here I won't draw a parallel with that, but what I'm saying is that you are taking the constraints and you are removing them one by one and plugging them into the objective, so that you are not increasing the objective. And the majorly beautiful thing is, by the way, this lambda is called a Lagrange multiplier. This appears in physics, this appears in childhood math. In class 9-10, we had read about Lagrange multipliers. Okay, so the main point here is, think of what happens when lambda is 0. Lambda is supposed to be a non-negative quantity. I am putting in that multiplier. I can have a program where lambda is equal to 2. So when lambda is 0, it's like I'm taking the original problem and forgetting about a constraint. Okay. On the other hand, if lambda is very, very, very large, right, then that means if you violate h of x, if you violate that constraint, you pay a heavy, heavy penalty. So if lambda is very high, then this problem becomes the earlier problem from the point of view of the feasible set. Okay. So bottom line is that all the takeaway, forget about, there are some niceties here which we won't be able to get through in 1 or 2 minutes. But the main point is that objective and constraints, there are some harder constraints. Don't get bothered, take the harder constraints into the objective. Okay. And this statement is what we said was, by taking this new old x in this new format, the objective function can only go down, but won't increase ever. So what that means is, and this is the most impactful statement here, is that the Lagrangian relaxation of the program O1 at any lambda is less than or equal to O1. So why are we talking about this? Because this is where inequalities come from. And this is where optimization stems from. So the normal optimization, convex optimization, linear programming, all of them use this kind of, this idea that given any, this statement is very powerful because for any lambda this holds. I have the choice, I have the freedom of lambda, and for any lambda this holds, okay? Enough of Lagrange. We'll use the fact about Lagrange multipliers, that there exists something that we can do with Lagrange multipliers. In the next 5 minutes, I'll solve one more and get to another question for the audience. So has anyone, okay, everyone knew arithmetic mean, geometric mean. Does anyone know Cauchy squares inequality? Cauchy squares everyone knows. And what's the easiest way of proving arithmetic mean, geometric mean? Some interaction would help. I have forgotten. Okay. Okay. So, okay. Given this statement, which we are having to prove, what does, is this Cauchy squares or no? Meaning, how far, is Cauchy squares a special case of this or no? So if I put P and Q to be equal to 2, then this becomes Cauchy squares, okay? So what we are talking about here is sort of a general form of Cauchy squares. Fine? Oh, okay, okay. Okay. The Cauchy squares inequality says x1 squared plus x2 squared plus xn squared, y1 squared plus y2 squared plus yn squared, square root of this is greater than or equal to x1 y1 plus x2 y2 plus xn yn. Okay, so this is Cauchy squares. It's a very, there are so many proofs of this inequality. This may not be a particularly illuminating form of understanding this, but you can think of this as, in this more familiar form, you understand, everyone knows linear algebra? Do you remember norm of a vector, or is that going too far again? Too far? Okay. 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 I'll do one more, and then I'll get back to the earlier talk. I'll just give you one puzzle. Okay. So this is essentially, it can be summarized as a 2 norm of x and 2 norm of y is greater than or equal to the inner product of x and y. That's the inner product. Okay. So, and this is a generalization of that. Holder's inequality is, that's what it's called. This is a generalization. Let me get rid of all this, and instead I want to say, if this is a proof you haven't seen, one should see this once. Okay, AMGM. I'm going to give a proof of AMGM. So first of all, AMGM for two quantities, A1 squared plus A2 squared, A1 plus A2 by 2 is greater than or equal to square root A1 A2. Okay. How do you prove this? Very, very simple. I am going to write A1 squared, A2 squared instead of A1 and A2. Okay. So this is just a transformation, if you like. Everyone okay with the fact that this is the AMGM for two quantities? Just that the two quantities happen to be A1 squared, A2 squared. Okay. By the way, this is Cauchy's proof. Cauchy gave this proof for the AMGM. So this is a statement which is very, very, very easy to prove. Why? Because the difference is A1 squared plus A2 squared minus 2A1 A2 is equal to A1 minus A2 squared. Agreed? And that is greater than or equal to 0. And therefore, you have the inequality. Now comes a next master stroke. AM greater than or equal to GM. So the next master stroke is this. So Cauchy says, hey, I'm going to try to prove it for 4 quantities instead of 2. Let me get rid of. I backed up on myself. Initially, I said, hey, I'm going to work with A1 squared, A2 squared, and then I reneged, and I'm going to be working with normal A1, A2, okay? So A1 plus A2 plus A3 plus A4 by 4 is greater than or equal to the 4th root of, first of all, this is a statement of the AMGM for 4 quantities. This is how Cauchy proves it. Cauchy says 4 is a multiple of 2, is twice of 2. So divide and conquer. Let me see if I can use this fact to prove that. So what he does is A1 plus A2 by 2 is greater than or equal to A1, A2. A3 plus A4 by 2 is greater than or equal to A3, A4. Fine? And now what he does is he takes these 2 quantities and takes the arithmetic mean of those 2. This plus this by 2 is nothing but A1 plus A2 by 2 plus A3 plus A4 by 2, the whole by 2 greater than or equal to square root A1 A2 plus square root A3 A4 by 2. Fine? This is the next step that he does. This already is the AM of the 4 quantities, A1 plus A2 plus A3 plus A4. Everyone okay with this? And what has happened to this? This again apply AMGM for 2 quantities, and thereby you get square root of A1 A2 A3 A4. Fine? Which is the 4th root of A1 A2 A3 A4. Fine? So thereby he proved 4. So next 8. Anyone take a guess about how 8 can be proven? Same, right? Partition into 2 and so on. Okay, so therefore in one fell swoop he managed to prove 2, 4, 8, 16. But these are powers of 2. What happens to the intermediate guys? So what do you think he does? So let's try to see what he does for 3. Okay, so by this he has proven for 2 and 4, but he hasn't proven for 3. So let's see what he does for 3. I shouldn't have erased the thing for 4. And this is the brilliant insight that I don't need to always go forward, because going forward I'm taking too many steps, 2 to 4 to 8 to 16. The steps are becoming larger. So therefore what he does, he comes backward. And this is called forward-backward induction. And this is what he does. So he says, I want a statement, I want this statement, A1 plus A2 plus A3 by 3 greater than or equal to cube root of A1, A2, A3. Okay. And somehow he really is obsessed that I want to get it from here. I'm not going to go anywhere till I get it from this statement. And now if you have fixed yourself that I am going to get it from here, then things surprisingly start becoming simpler. Because you have sort of forced yourself that, hey, this is what I want to do now. So therefore he says, okay, I need to set A4 to be something. I need to set A4 because this statement is about only 3 quantities and there's a extra 4th quantity here. I need to be setting it to something of the 3 quantities. And if you play around a little bit, if you see the final solution, it seems the most natural thing. But I guess you have to play around to get to that. So what Cauchy does is, he says, this is symmetric in A1, A2, A3. This is also symmetric in A1, A2, A3, A4. So therefore, whatever I set for A4 in terms of A1, A2, A3, I should make it symmetric. I should sort of make it symmetric in A1, A2, A3. And then he says, okay, I mean, you can, so if you had more time, you could try first with this. And then you will see this does not give you really what you want. So after a couple of tries, you say, okay, what about by 2? But once you have started doing this game, that by 2, then the most natural thing which comes about is that there are 3 quantities here, why not by 3? And that's what we want. Meaning, we want some expression of this form, so therefore, why not force fit that? And now let's put a1 plus a2 plus a3 by 3 in this statement. So that becomes a1 plus a2 plus a3, and overall there will be a 4 plus a1 plus a2 plus a3 by 3 greater than or equal to the 4th root of a1, a2, a3, a1 plus a2 plus a3 by 3. Everyone okay with this? What Cauchy did here is just that. So now appears the beauty. This and this are the same, and 1 plus 1 over 3 is 4 by 3. So therefore this expression on top is 4 by 3, a1 plus a2 plus a3 by 4. Beautifully, what has happened is the 4 has, meaning that pesky 4 from which I had to go to a 3, the 4 has now vanished. Now what you have is a by 3. And what has happened on this, there's a pesky 4 here too. 4th root of a1, a2, a3 and a1 plus a2 plus a3 by 3. Fine? So this 4 goes away, and now this expression becomes by 3. Everyone okay with this? And now what you do is, you have something here which is the same thing here. Here it's under the 4th root. So you take the 4th power, and then you have 4th power here and 1 power here. So you cancel this out, and you get a 3 here, and then you are home. And that's it. So what he did was, he went forward. This is for 3. Similarly for 5, what do you need to do? You need to go to 8. And then you need to set 3 of those quantities equal to a1 plus a2 plus a3 plus a4 plus a5 by 5. Okay? And that's the proof of AMGM. From where to where? The next step. So there was, so what we said was there was a 4th power, and I'm just repeating what was written here, right? Right? So this was, till this point is clear, this is just a restatement of what's going on. And now I want to simplify this expression. I want to simplify this expression by taking both sides to the 4th power. So to the power 4, this goes away. And you see one extra term here which can cancel with one of the terms here. So then you make this vanish, place a 3 here, and now to get it in the form of AMGM, you take the cube root. Okay, and that's okay. So how much time? I think I'm almost done or something. Okay, so bottom line, I don't know what happened to the motivation here. The inequalities are really important, and more so they are really, really beautiful. But you need to engage with them. It cannot be a sort of idle activity. But once you start engaging with them, they are really, really. I am going to give you some. Okay, forget that. I'm just showing you that I did create the slides. Okay, and by the way, do read this book. This book is an awesome book. Cauchy squares is so important. There is a book on that, and the book is an amazing read. I mean, really nice read. Sample applications are, you can try this for yourself if you wanted. This one is x squared plus y squared plus z squared. So, and then this one is a famous inequality called, all of these are a small step away from Cauchy squares. So, and then other inequalities which are there are, meaning I want you to get impressed about the importance of inequalities, because even in an area called like crystallography, in statistics, Kramer-Rao is actually an application of Cauchy squares. So it finds use everywhere. So if you wanted to learn one thing about math, it better be inequalities. And if you wanted to learn optimization, you should learn Lagrangian relaxation. And the two are connected. So forget that. This is another quiz problem, but yeah, or prove this. Okay, any questions?
So, does anyone have any question? Okay, so since we are running with a tight schedule, maybe if someone have any question, you can take it offline. Let's thank our speaker once again for the fascinating talk and teaching us inequalities. Thank you so much for coming, and thanks. We hope you'll come next year as well. This is a